Hey guys, my name is Vivek Sharma. Today we can cover this interesting problem that's called the recover binary search tree. So in this kind of the problem, we want to recover the binary search tree, and there are two values that has been swapped by mistake, right? So let's try to take some examples from the examples, right? So it's like 3, and then it's 1, it's 4, and then let's say it's 2, right? So we can see like 1 is less than 3, so this is good. 4 is greater than 3, that's good, but 2 is less than 4, so it's correct position from the 4 perspective. But if we see 3 is greater than 2, so basically it should be uh, in the between like 2 and 3 and 4, so 2 is not right. So 2 should be greater than 3, and in fact 3 should also be this value should also be less than 4 because of the binary search tree property. So in the binary search tree, left child is always less than the root and right child is always greater than the root, right? So we know that this position, if we swap these two elements 2 and 3, we put 2 here, and if we put 3 here, then I think we should be good, right? If we swap these two elements. So to solve this problem, first of all we need to find such elements. Not they are not in the correct position, right? And if we find those values, then we can just go ahead and swap, that's it. And if we swap, then we don't need to restructure our binary search tree, or we don't need to play around here and there with the pointers. We will just simply do the swapping of the values, right? So the first step would be to find the values, second step would be to swap the values, right? So to find such values, if you can recollect the algorithm of validating the binary search tree, right? So once we validate the binary search tree, we follow some where there is a might be multiple ways to validate the binary search tree, but the straightforward way might be the in order traversal, right? So in the in order traversal, because in order traversal gives us the sorted tree, sorted array, so that we know that 1 is always less than 3 and 4 is always greater than 3. And if we violate this rule during our in order traversal algorithm, then we know, okay, this is not validated, this is not the binary search tree, this is not the valid binary search tree, right? And that's why we can easily use the in order traversal algorithm to validate binary search tree. So if you are not familiar that how to validate binary search tree, I would recommend that first of all take a look on that algorithm, that how to validate binary search tree using in order traversal, and then come back to this problem. It will be straightforward, right? So let's first of all try to create the placeholder for the validated binary search tree, and then we will go from there, and we will see that how we can find these two problematic values, right? So let's say I creating some in order traversal here, right? Let's say this is private void in order root, right? So let's say if root equals null, go ahead return, and this is root dot left in order. There is some typo here as well, root dot right. All right, so we need to take some previous as well, and the reason is that that's how we validate whether it's a valid binary search tree or not, right? So let's do that as well. So let's come here on the whiteboard and let's see. So let's start from 3, and we will go to the left, and left is 1, right? And if as per algorithm, before going to the right, we are storing to the previous, right? So in this case previous would be 1, right? And after coming out from the recursion, because left is null, right is null, then it will come out from the recursion, previous would still be 1, and then it will go back to the 3. So 3 is the root, and it will check like 1, it is less than equals to 3, then it means it's valid, right? So we can check the reverse. If previous is greater than equals to 3, then it will be invalid binary search tree, otherwise it will be valid, right? So we can put the same condition here as well. We can check like if previous is not equals to null and previous dot val is greater than equals to root dot val, then this is invalid case, right? Go ahead and return, means invalid BST, right, as we saw in our whiteboard. So in this case previous is 1 and this is less than equals to 3, so it is valid. But if it is, we are checking reverse condition, then it will be invalid binary search tree. So let's go to the right hand side and let's figure it out the same thing. So let's say this root is 3 now, right, and then we go to the right, and so once we go to the right, then we are storing as a previous as per our algorithm, right? So before going to the right, we are storing previous as the root, so our previous now in this case is 3, right? And then we go to the right and 4, and then we come back again, and then left is 2. So now the root become 2, and now previous is greater than equal to 2, right? So previous is 3, root is 2, and previous is greater than equal to 2. 3 is greater than equal to 2, means this is the invalid case, right? So if we have those conditions, then when we can easily figure it out, what is the problematic values, right? So in this case problematic values is previous, right, and the second value is itself the root, right, as per our algorithm, right? So if we know these previous and root, just get those values and just swap those values, that's it. So let's go ahead and do the same thing. So let's take first and second as well, right? So let's add those conditions. If first is null and itself is previous is not equals to null, or let me just expand it a bit, then what we want to do, we found already first, right? So in this case first will be our previous, that's what we saw from the diagram, right? And to find the second, we need to make sure that we already find the first, right? If we did not find the first, we don't want to find the second. That's why I put this condition that first is not equals to null, then previous is not equal to null, and then previous dot val is greater than equals to, so this would be the same condition, right, of the invalid binary search tree. And in that case second equals to our root, right? So if we see here, this is the first previous, 3 is previous, and root is 2 in this case as per our algorithm. So if we find these two values, then we just have to swap, that's it. So let's go ahead and swap. So first dot val and first dot val equals second dot val, and second dot val equals to temp, and that's it. So this should I think this should work. If we talk about the time complexity and space complexity quickly here, so time complexity will be order of n because we are traversing all the nodes. Space complexity would also be like, if it is flattened binary tree, then it will be order of n in the worst case, right? So if tree is flattened, right, else it will be log n or h, right? So for the average case would be log n or h. So let's quickly check for the compilation error first of all, and if it is getting compiled, let's try to submit this. Okay, so there is some problem, and let's see what's the problem it here. So this is the input 314, and let's try to figure it out. Okay, so let's see, and let's see what did we miss it here in our algorithm. So let's see, we are doing the in order traversal, in order dot left, previous equals to root, we are going to the right. Okay, so this actually you know what, whenever we are doing previous, this block should be the above than previous. So this is, I mean, this failure is for the good, so that we don't forget this important step. So I was assigning the previous before this block, and that is that will create the problem, of course. Why it will create the problem? Because we want to track from the previous. So if we go to the whiteboard, previous we tracked in the 3, and then we are going to the right, and then we are going to the left, but still we are having the track of the previous. So we want to track the previous before going to the right, and after going into the loop again, then we want to check the previous that we persisted earlier, but we don't want to corrupt the previous value, so it should be here. So let's try to run it again and let's see. So I think it should be good now. Okay, cool. So looks like it's working, and don't get confused with the error that I just showed, because it's really uh, not a point of confusion, because always we want to assign this previous before going to the right, and we earlier I put this previous before this block, before the selected block, and that was wrong, because we don't want to corrupt this previous value, right? We always want to have this previous value tracked basically from the previous iteration, not in the current iteration, right? And that's how this binary search tree is also, we are just drawing run from the whiteboard. Hopefully this was useful. uh, just let me know your comments, feedback, or if it was not clear. Thanks a lot. Bye.